Hello friend, thanks for stopping by my channel. Today we will be discussing a new topic in data structures, and we will try to solve one problem on LeetCode which uses that topic. So that particular topic is graph. Before we jump into what graphs are and how they are a very useful data structure in computer science, we will try to first go through a simple problem on LeetCode. So let's go through the description of the problem. This problem is known as course schedule. So you have total of num courses, the number of courses that you can take, which are labeled from 0 to number of courses minus 1. You are given an array called prerequisites, where prerequisites is a pair, AI and BI, and that indicate that you must take course BI first if you want to take course AI, which means if you have a course pair like 0 and 1, that should indicate that to take course 0 you have to take course 1. Now what we have to tell is, given a set of these prerequisites, we have to tell that if I can finish all the courses, if I can finish, I'll return true, otherwise I'll return false. So that's the return type of the function, is boolean. And the courses here, it's a sample example, like if number of courses are only 2 and you need to take that in that particular order, 1 and 0, then there are total of 2 courses that you can take. So to take course 1 you should have finished course 0, so it is possible you will just take 0 at first, then you will complete course 1. But suppose you have course dependency like number of courses like 2 and your prerequisite something like this. So the problem is there are 2 courses to take, but to take course 1 you have to go take course 0, and to take course 0 you have to finish course 1. So it's from the description it seems like a very simple problem, but let's try to visually understand what we are trying to achieve here. So a visual representation of graph, it's something that we have noticed in some of the data structure also. So that data structure is called tree. So we had a couple of sessions where we discussed about different kinds of trees. For example, we have a tree like this, where this 2 is my root node, and then it has 2 children, its left children and its right children. So this is a tree data structure. But it can also happen that there is a node connection between 3 and 4. In that case, we can't call it a tree because then it becomes a cycle. So this 2 is connected to 3, and then 2 is connected to 4, and 3 is connected to 4. So this is called a cycle, and this cycle cannot exist in a tree because, as we have seen, the trees, so far the trees that we have covered were only binary trees, but a tree can be of any array or n array tree that we call it. So it can be something like we have 3 children for that given tree. So this is also a valid tree because what happens, there is a no cycle in this particular tree. So what is a tree? A tree is a special type of a graph, which is a graph with no cycles. So cycles are connections like this, where if you have n number of nodes and they are connected within each other. So that's why we cannot store the data for graph like how we store for tree. So usually for tree, we store it in something like this. We have a data structure where we have a value. This can be of any type. It can be of integer, it can be of string, or anything. So this is basically the data that we are storing here. So in our particular tree example, it will be an integer. Um, and it should also contain a tree node left, and this entire structure itself is a tree node, and it will also contain a tree node, right? And this is a standard structure for a tree. And then you can have some constructors and stuff like that. But a graph, it cannot be stored in such a way. Actually, even a tree, instead of having just left and right, so this is typically a binary tree node, you can have sort of a list of tree node structure, a list of tree node structure. So let's see if we represent a tree in that particular manner. So suppose we have a tree like this. So let's actually bring this tree over here. So let's bring this entire tree to this side so we can work on it, and we can remove this one. And so let's say we have a tree like this, and the data structure that we are using to save the tree, it's not a binary tree, so we can't use that explicitly. Two tree nodes will be there. So what a tree node will basically contain, it'll have an integer value or val, anything it can be named, and then you have a list of tree nodes. So this list is a free form list. So you can have one node, you can have three nodes, you can have zero nodes, any number of nodes you can add to it, which we'll call children. So this representation becomes much simple, and we can use this representation for saving a binary tree also. So suppose we did not have this third node. So suppose we did not have this third node, none of the values were there. Then also we can use the same representation. We can just store the data. So the data will be stored like this. So every node, the structure, you will have something like this kind of a structure. And inside that you have the data. And then you have a list of element. And this list of element, you'll have something like this. So that becomes the structure of our tree. Like the first root node will contain that, and then this one will point to this data. So there will be, say, another data block down over here. This data, this data will contain just the value 3, and then an empty list because it does not have any children. And then we have another data bag, sort of, which will have the element 4, and then we will have another empty list. So this becomes our new representation of the tree. This is not how usually we write binary trees, but this is very well possible. And if you had connections like this, so it's like a three-way tree, all you had to do was you can erase this, and you can just put this element here, and now your tree will work the way you have. So one thing to mention is, like, whatever the data we are putting here, this is not actually value. So just to represent this, we can show something like this: pointed to 3, pointed to 4, pointed to 5, something like that, because it's actually a tree node type. It's not an integer type. This value is an integer. This is just the value that we are holding, and these are all pointers. So this guy is pointing to this one. This guy is pointing to this one, and then we'll have another data bag here where 5 is stored and the list of the elements, and this one will basically point to this one. So what's the point of going through all of this? So the point is, this particular representation is called an adjacency list representation, where you are, so instead of thinking it like a tree, we think we have all the nodes which are adjacent to a given node saved within the data structure for that node. So for that node of 2, we store all the adjacent elements 3 and 4. By adjacent, we mean they are connected some way. So instead of looking it like a tree, we can look it like a graph. So this representation is like a major implementation of how we implement graphs. So now we can see that how we could simply starting from a binary tree representation, we have changed our representation of a tree to an adjacency list representation. And this representation can be used to showcase a graph data structure. And the good point about this data structure is it can also support cycles. So this data set is a valid tree data set, but suppose we have nodes like this, say 3 to 4 and 5 to 4. So then what will we have? We have in this particular case, so we are sort of saving nodes to 3, edges to 3, edge to 4, edge to 5, something like that. So from here, we will have edge to 4, which will again point to this one. And in 5 also, we'll have edge to 4, which will also point to this one. So now it does not contain a cycle, but it's not truly a tree because still you have connections between these nodes, and it is actually a cycle because we just consider directed edges. So these are directed edges, like you can think of like a one-way highway, so you can go in only one direction. But it can also be like bidirectional. So you can go from 2 to 3, you can go from 3 to 2. So in that case, what we had to do was, so these will be similar, like you'll have pointers like this. Here, instead of just pointer to 4, we have to make some modifications here. So let's actually erase this part. Let's erase this part. And also erase this part. So the representations become 3 is now connected to 2, 3 is now connected to 4. So all the nodes I have edge with. So I'll save that. So this will point to 2. This is already pointing to 4. So this is not required actually. And 4, it'll have connection to 2, it'll have connection to 3, it'll have connection to 5. And then 5 will have connection to 2 and connection to 4. So now you can see that this becomes like a graph structure and we can save all the different nodes here. So now let's actually clean up this example and come to the question that we have. So the question is scheduling course, like how we can effectively determine if we can take the number of courses. So if we have courses like 0, 1, 2, 3, so we have 4 courses, and these courses we can think of, they are drawn like something like this. They are drawn something like these nodes. So you have these courses, and now we define the prerequisites. So the prerequisites are defined in such a way, for example, in this direction, like to take 1, you have to take course 0, and also to take course 2, you have to take course 0, and to take course 3, you have to take course 1. So see how this thing can be represented in that adjacency list kind of format. So first of all, we'll have all the places for the data. And so this is like the data slot. And then you have a list slot. So what we will have, the list slot for 0. So list slot for 0 in adjacency list, we are basically just keeping what are the courses that we depend on. So 0 does not depend on anything, like nobody is pointing to 0. So it won't have anything there. It's like what are the courses that are prerequisites for this particular course. So for 1, there is only one prerequisites, that is 0. For 2, there is also one prerequisites, that's 0. For 3, there is also one prerequisites, that's 1. So now if we want to find out which order that we want to take, we can figure out something like this. So we can say we have to take course 0 first, then we can take either course 1 or 2 because both of them are just dependent on 0. So you can take any of them, but only after you take 1, you can take course 3. So this is the order, like either you can take 0, 2, 1, 3, or you can take 0, 1, 2, 3, or you can take 0, 1, 3, 2, something like that. So all the possible combinations that you can create out of this order. So this is basically our problem. We actually moved a little bit advanced here. Our problem is quite simple. We have to just tell if it's possible to take all the courses or not. So in what case it's not possible to take all the course? That scenario is if we have a cyclical dependency. So for example, we have course 0 and 1 and 2 and 3. What happens if you to take course 0, you also have to take course 1. So then it what becomes, you can't take course 0 because to do that you have to complete course 1, and to take course 1 you have to complete course 0. So it's like a deadlock scenario. So this situation is very bad, and in those cases we can't complete the course. So now let's see how we can solve this problem using the graph data structure. So let's come here and we'll try to draw these nodes a little bit cleanly. So we'll have those values here, 0, 1, 2. Let's have only these three, and the dependency is like this. And then you have dependency like this. So first of all, I think we are clear that we will have the representation as the representation will be something like the adjacency list representation. And now for each of the nodes, we have to do a traversal, or in graph terminology, it's called TFS, which stands for depth first search. So we have to do a depth first search here. By depth first search means suppose we have nodes like this, and then we have node like this, 3 here. So we'll go in depth first. So we'll go to 0 to 1, then 3, as much depth as possible, and then we'll come back and visit 2. Instead, what breadth first search, there is another kind of search algorithm called breadth first search, which instead of going into depth, it'll just first cover the breadth, then it will cover the next breadth, and so on. So, but in our case, we'll just follow a depth first search. In this particular case, what we'll do is we'll keep on traversing this graph, and what we will say is we'll try to mark those nodes. So how we will mark them? So let's actually clear this canvas because I think we have a lot of clutter here. So we'll try to mark those nodes. So suppose this graph 0 is there, we'll create a bigger circle here, and then we have 1, and then we have 2. And the dependency is something like in this order. So take course 1, you have to take course 0. So suppose we have the first node. So this node, whenever we go to that node, we will put a tag called that I'm visiting you. And then what we will try to see, we'll try to visit all the nodes which are prerequisites of this one. So 0 does not have any nodes of prerequisites, there is nobody pointing to it. Then we will mark this node as visited. So which means this node is self-contained. Then what we will do is we'll go to the next node. And this is not actually traversing from here. It's something like we have the list of all the courses. So, and we're going one by one. So first node, we mark it as visiting, then we have marked it as visited. And then we go to point number 1. So now 1, here we say it's also visiting. And then we see its prerequisites. Its prerequisites is also visited. And then we mark it as visited. Similarly for 2, that also gets visited. And if everything is fine, we'll just, so all of them are same, we'll just say return true, which means if nothing happens, it's fine, we can finish the course in order. But what if we have a dependency like this? So in that case, what will happen is you have first coming to this node 0, and this node is in state visiting, and then we go to the its prerequisites 1, and this node also has a dependency on this one. So what we'll try to see is if the node it depends on, that's also in the visiting mode, which means we have not completely visited that node, then we have to say it's not possible. We have encountered a cyclical dependency. So only if all the nodes that we point to they are visited, then we can be sure that it is fine and there is no cycle in this particular graph. So let's actually try to see how this works out in code, and it'll be easier for us to understand the concept. So now we will switch back to our editor. So for editing, we are using VS Code, and for building, we are using Gradle. This gives us a very lightweight, simple environment where we don't need much debugging information, but all we need is write simple code, see some output, and do everything via print line. So that's our sort of a challenge that we have put to constrain ourselves. So now let's go back to our LeetCode folder. We have created a lot of folders. Here we'll try to create another folder for graph, and this is actually within LeetCode. So within graph, we'll create course schedule.java. So here the first thing we'll put it under the same package. We'll have the class name, and first we'll create the test method, public void test, and in our app.java we will point to this course schedule classes test method. And now let's actually get the function signature from LeetCode. So we'll get the function signature over here, and the function takes number of courses and then prerequisites. What we need some auxiliary data structures. So one data structure we need is a hash map. So hash map is the dictionary which will hold the values. So you can think of it's like all the integers or all the courses will be saved in the key for the hash map, and the value will be an array list of integer, and this is my entire graph structure. So this graph is basically written in that adjacency list format. So we'll do a import java util hash map and import java util array list, right? And we'll also have two indicators, like, well, those indicators won't be changing, so we'll call them visiting and visited, and they are 1 and 2, so that also seems fine. Now we come to our can finish method, like can we finish the courses. So the first thing that we have to do here is build the graph, because we are not given a graph, we are given the number of courses and the prerequisites. From there we have to build it. Once we build the graph, then we sort of actually that's two parts to the graph creation. So let's just do the first part. So the first part is take the number of courses and put the number of courses in our graph. So we'll do graph put new array list empty here. So for each of the courses, we'll create a new array list and put it onto the graph. Now coming back to the next section of building the graph, we have to use the prerequisites. So the prerequisites is an array of an array. So we can do a for each something like this. And then what we can do is for pair 0 at pair 1, right? So this basically means we have the graph 0 and graph pair 1. So the prerequisite is an array of an array, and each array, like each element is an array there. So that is a sort of a pair element, and the first course, to take the first course, you must complete the second course. So that's why we are getting the graph element by pair 0 and then adding to its list, like that gets added to its prerequisite list. So you can think of the list that we are putting here, it's the list of prerequisites for any given course. That course is represented in this integer format. So now you have completed this graph structure here. What we have to do now is we have to traverse the graph for all the courses, and we have to see if we can take them. And the way we'll determine if we can take them is by doing a DFS visit. So by doing a DFS for I, and DFS will have a return type. If the return type is false, then this will basically execute as true because I'm doing a not here, and will return false. So if the DFS call return false, then I can't complete the course. Otherwise, if the DFS calls always return true, then you would never hit this part, and at the end we'll just say return true. Now we have to implement this DFS method. So let's actually try to do that. So the DFS can be a private method. It can be a private Boolean DFS integer, let's say u. And here what we need to also have is graph state, because we are only saving integers. We need to have another data structure for saving the graph states. So that state will be saved here. We can just call it states, new hash map. And what we need to do is first, whenever we are going into the DFS method for any integer u, which is this u basically is the course that we are taking. So we can actually call it course rather than call it u. That's actually a better naming convention. So we can do states dot put for course visiting. So we are just visiting for the course. Now for all the prerequisites for this particular course, which we will get from the graphs this way, what we have to do is first we'll do an integer number graph get course get I. So get the course, or what is the prerequisite. We can call it, instead of number, we can call it prereq. So that's my prereq, that's under consideration. What I have to check, if states contains key prereq, if states does not contain the key prereq, then we have to visit it, because states does not have the key means that we have not touched the node whatsoever. Like we are not even visiting, we are not even visited. So we have to do a DFS that there also for that prereq. And if the same thing, if it returns false, then we'll return false, and it'll just call back one step up. And if it returns false, the final can finish function will also return false. Else, if it sorry, if it's already containing within the states, so that can be another scenario. So states prereq, that's equal to visiting, which means there is one of the prerequisites which I'm still visiting. So that is also not accepted. If I have all the prerequisites, I should have completed all the prerequisites before I come here. So it's not possible to do that. I end up in a cyclic dependency. Like I have not completed my prerequisites and I'm still taking the course, which is not possible. These are the two scenarios that we have to take care. Otherwise, once we come out, what we will do is we'll do put course visited, and we'll return true from here. So now let's actually try to see, run this for some examples. And we'll also put some debug statements so that we can see how the execution is sort of going on. So first let's try to do can finish. Can finish actually has number of courses and prerequisites here. So we'll have a new integer array, and it's a two-dimensional array. So it'll be something like this. Say we have two courses and we have just one prerequisites. Then what's the output that's coming out of it? Let's clean this command line and try to run it and see. So in this case, what we are expecting is true. But let's first see if our code compiles and if we are able to successfully run. So there is some error. What it is saying, it's saying illegal initializer. Okay, yeah. So it has to be an array of array. Let's try to run again this time. So we get true, which is expected. But is that correct? Let's see. We'll put some debug statements here so that we can understand the flow. So all the debug statements. So this is fine. I think building graph is simple. What this is also fine, which we can just put a debug statement, something like we are in can finish for I. So when this prints out, we can say like we are entering into the TFS for this particular course I. Now, once we are inside this TFS, there will be this for loop. Inside the for loop, there are two conditions. If the states contains key, so we can do like dot println states dot contains key prereq. So in here, state does not contain key. So state does not contain key. That's why we are here. And instead of putting the debug statement there, what we can do is we can just put it here whenever we are entering the function instead of whenever we're calling the function. Whenever we are entering the function, we'll just tag it like this, dfs, and we'll say course. So whenever we are entering the function, we'll know that this is where we are entering. And actually we'll need also one way to know the difference between different courses. So we can have still this also. The reason we can have it in two places is this will be called only once for each of the course, but this DFS will be called multiple times because we are calling it recursively inside also. So that's why this statement will hit multiple times. And then we come here and we'll say states.get prereq is visiting. That's what we put here. Right, let's see what are the outputs that we are getting for this input. So first, can finish 0, we enter into DFS. It does not have any dependency, so this for loop basically executes cleanly, and we do states put this and return true. We can also do this. Something like this, and we can put some more debug statement. DFS. Sure. Let's try to run again. Uh, yeah. So we see that DFS is visited, then we go to can finish 1, then we enter into DFS 1. We enter into the loop, but the prerequisite is neither of them. So neither of them. So we can say else is like a system.println. We can say DFS for loop and just tell which iteration we are in. So we'll just tell I. So now if we just print it out, we can see the differences between for 0 and 1. So for 0, this statement did not execute. So we did not go there, but for 1, it actually did. We went there. And now if we just increase this example to include this particular case here, like you have 0 to 1 and 0 to 2. First, we'll try to see what happens there. So we have we'll add just another prerequisite, and there will be one more course. So this should be 3. So we have 0 to 1 and then 2 to 0. Let's clean it and run it. So we have can finish 0 first. So DFS 0, it becomes visited. Then can finish 1, DFS 1, DFS for 0, and DFS 1 is visited. And then we have can finish 2, DFS for 0, DFS 2 is visited. So this is actually a very clean way it's executing. Now let's see actually one example where it's cyclic. So I'll keep this and add one more cyclic dependency where 1 is dependent on 0. Now let's see what happens. So we'll run it and we'll see it's getting output as false. And why are we getting false here? So first we get 0. We enter DFS with 0 and states contains key. Yeah, so it's 1, which means it's visiting. So 0 is visiting. And then we call DFS for 1. So DFS for 1 is there. And now again, we hit the same thing that, sorry, let's actually get here. Correct. So at the first time, we don't have anything in states. So we enter here and call DFS for prerequisite one. And then we go to states get where it's set to visiting for 0. So that's why it's executed here. So the first time we go for 0, that time we call for 1. And but while doing for 1, we encounter that 0 is already in visiting state. So it's an invalid scenario and it's a cyclic dependency and we call it out. So let's actually replace all the system.println here with comments so that we can submit to LeetCode, and adding more log statements diminishes the performance, so we don't need to submit with logs. And this seems fine. I think the output also is hidden, that's why it's not printing. But if we just do that, it's showing false, so that seems fine. Let's actually copy this part of the code over to LeetCode. Right, and then we'll try to run this. Seems fine. We'll try to submit it. Seems fine. So that's all we have for today. Thanks for joining in. See you in the next session. Bye bye.